A key skill that we need to look at when thinking about the Euclidean algorithm is we need to know about the divisibility of numbers, the notation associated with it, and some of the theory behind the ideas that get brought up with this. Now, when we are talking about divisibility, there's a couple of key things I want us to remember. First things being that if B divides by A, what that means is that there exists a C, so another letter belonging to the integer value such that A is equal to B times that C. So A is some multiple of C if B divides it. And if B divides A, it is called a factor of A, also called a divisor. Now if B divides A and C, so going back to this premise here of the A equals BC, if B divides both the A and the C, it's a common divisor of the numbers A and C. Now what we have to be able to do is find the greatest common divisor. So the greatest number that divides both of those. So for example, if I had 8 and 24, the greatest common divisor of both of those is 8. It's the biggest number that goes into both of those numbers. If I had 12 and 18, the greatest common divisor for that is 6. 6 is the biggest number that goes into 12 and 18. So that's what the greatest common divisor means. Now, if there's a number greater than 1 and has more than 2 factors, this is what's called composite. Now, this will be the product of at least 2 prime numbers. So any number that has more than one factor like that can be broken down into factors which exist for prime numbers. So for example, if we had 12, we know that 12 is equal to 6 times 2. So there's 2 factors. Now 2 is a prime number and we have 6. Well, 6 itself can be written as 2 times 3. So what we're then able to do is break down 12 as being 2 times 2 times 3. So the product of 3 prime numbers together. What we're able to do is we're also able to say that multiplying the set of natural numbers will give us a set of numbers which are generated in multiples of A. So multiplying the set of natural numbers will give us A, 2A, 3A and so on, which just generally build up a set of numbers which are all multiples of that initial number, in this case what we're calling A. If we have n1a equal to n2b, so n1 and n2 are natural numbers, they may be different, they may be the same, then n1a and n2b are common multiples of a and b. So generally speaking, we're more interested in the lowest common multiple of the two numbers. So this is just some of the key ideas that we have to bear in mind, particularly things like the greatest common divisor and the lowest common multiple. They are key facets that come into play, particularly with things like Euclidean algorithms. Now there's a couple of bits of notations and properties we have to make sure we're aware of. B divides A, this can be written in this format here, so B vertical line A. And if it does not divide A, then it's written as B vertical line A, but the vertical line has a line going through it. And it leads us on to 4 key things that we have to bear in mind. So the first one is that if A divides B and B divides C, then A divides C. And this is actually quite simple to prove, because if A divides B like that, what that means is that B is equal to something called AN. And if B divides C, what that implies is that C is equal to something, let's call it M times the B. But we know B is equal to this A times N. So I can plug that in and then say that C is equal to M times N times A. So this Mn will just be another natural number, which is the product of the two numbers M and N, which means it's a multiple of A. If A is divisible by B and A is divisible by C, then what we're able to say is that A is divisible by B plus C. So again, let's go back to this initial theory. So let's take this idea again, that if A is divisible by B, B is equal to AN. And in this case, what I'm also going to consider is that if A is divisible by C, what that then means is that C is equal to some multiple, let's call it M, times A. So what that then means is that B plus C is equal to AN plus AM. Can take it a factor of A for both of those. So it's n plus m times a for those. What that means is that n plus m, because it's a set of natural numbers, so n and m both belong to that, we can say that this holds true. That a is divisible by b plus c. What we also know is that a divisible by b means that a is divisible by bc, so the product of two numbers where one of them is the same. So for example, if a is divisible by 2, then a is also divisible by something times the 2, so some sort of product there. What we're also able to say is that if b plus c is equal to some further variable, let's call it d, then a is divisible by b and a divisible by c. What that implies is that a is divisible by d. What we can also say is that if a is divisible by c and a is divisible by d, that implies then that a is divisible by b, given this relationship here. So all stems from that. So these rules of divisibility are things that we need to bear in mind. They're key facets and key properties that get used in the work that we're doing and the work we're going to extend it into when it comes to the Euclidean algorithm. Now I've got one thing for you to consider just to show you how this might come through and the way we need to think about problems involving them. So let's consider the equation x squared plus 2xy plus y squared equals 0. And I've got three things I want to look at. First, I want to explain and consider why there exists an a belonging to the group Z such that y squared equals ax. I then want to discuss why there exists another letter called b belonging to the same set of numbers such that x squared is equal to by, so x squared is a multiple of y. I then want to explore the solutions to x squared plus 2xy plus y squared there. So let's imagine I'm going to start by looking at a. Now, there's four terms in the equation. What we can say is that since x is divisible by 0, and x is divisible by x squared, and x is divisible by 2xy, so we can take this and do that for each of the terms here within the equation, then what we've got to do is by the previous result above, so the one where we had b plus c equals d, what that then means is that if a is divisible by b and a is divisible by c, then a is divisible by b plus c. So using that previous result that we came up with a second ago, what we can then say is that x is then divisible by y squared. So what that then means is that since x is divisible by y squared, there exists some a within the set of integers z such that y squared is equal to ax. Now what we can do is then look at it similarly in terms of the y. So let's explore the y variable, because that's what we're looking at here for some multiple of y. So if I'm going to look at the y variable, similarly in the same fashion, what I can say is that since y is divisible by 0, and y is divisible by y squared, and y is divisible by the 2xy as well. What that implies, again, using this b plus c equals d property that we had there, is that in this case, y is divisible by x squared. So because of this, that implies, because y is divisible by x squared, that implies that there exists some b belonging to this set of integers z, such that x squared equals by. Last part was to then explore the solutions to that equation there. To explore the solutions. So let's imagine we're going to take this and we're going to treat it as a quadratic in terms of x. So if that were the case, we'd imagine it was written in the format ax squared plus bx plus c equal to 0. The only difference being when we compare it to this here, the b would be given by 2y and the c would be given by the y squared. If I did that and then I looked at the quadratic formula and plugged it all in, I'd know then that x is equal to negative 2y plus or minus the square root of 4y squared minus 4y squared all over 2. If I was to simplify that, so I'd have negative 2y over 2, so the 2's would cancel. Then plus and minus this, so I'd look to cancel a 2 here, but 4y squared minus 4y squared is 0. Square root of 0 is nothing, so I'd then end up with just negative y. So what that then implies is that for this equation here, the solutions are given by x, negative x, for all x belonging to the set of integers z. So what we've done is solved it in terms of x, seen that x can be represented by negative y, so if negative y equals x, y equals negative x, and any coordinate which was x, y can be given by this and is a solution to the equation. So when we're thinking about these numbers and when we're thinking about the relationship to one another, we have to check the relationship in terms of divisibility. How do they relate to one another in terms of that? Is A divisible by B? Does that mean we can then draw up some relationship between A and B where they're multiples of one another? And will that help me in my long-term algebra and calculus when it comes to the scenario? Will it help me when I'm exploring the solutions to the equation that's given there? So we have to ask ourselves these questions as we're working through this material, as we're working through what the questions are asking us to do, exploring solutions to various different equations, and breaking down questions such that we can make them into a much easier format, or a format that we're after, and we can use them in further operations from that.